So we're going to continue now with this going from the simple design. So I want to go back to my whiteboard. And so basically we said we have an experiment in which the temperature, its curing temperature is changing from 100 to 130 to 160 and to 200 degrees C. And the time of curing is from 1 hour to 3 hours and 5 hours. So basically, if you think about it, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. But initially, the path in the simple design approach that we had taken was basically first at 100 degrees C, we test the cases. So we had 3 cases, and we realized here's the best performance, and then we added with another 3 sets of experiments. So 3 plus 3, 6 experiments. This was the simple case. And and what we said was that the problem there is that the best performance, although at 3 hours is here, at 100 degrees is after 3 hours, at let's say 600 could be at after 5 hours, and we just don't know it. So what is a more reliable way to do the experiment? Well, a more reliable way to do the experiment is basically to test all of these cases. This is what we call the factorial approach. And so obviously the number of experiments that we have to do in this case is we have 2 factors. And this guy that I call it N1 is equal to, is equal to 4. And this guy that I call N2 is 3 cases, 1, 2, 3. So the total number is N1 times N2 is basically 12 cases. So here, so basically you can, now if I go back to my slides, which is here, in the factorial case, we are going to experiment all the possible cases, all possible cases. So if we have n number of factors, that factor 1 takes n1 different cases, and factor 2 takes n2 different cases, and factor 3 n3 different cases, and factor 4 or factor I n I different cases. And all together we have k factors, which gets the kth one will take nk. The total number of experiments is n1 times n2 times ni times all the way to nk. That's the total number of experiments that we need to do for this experiment. So here in the experiment we did, we had only 2, and 1 was 4, and 2 was 3, so that was 12. So right away you see that in the factorial case I have to do 12 experiments, whereas in the simple design experiment I have to do 6. So I'm paying a lot more price, and this can actually go up a lot faster. For instance, so basically the total number of experiments is going to be the product. This is equivalent of sum, but instead of sum is product of all these ni cases. So for instance, if you take, you want to understand which flight performance is the best, you take 5 cases of horizontal tail, 4 cases of vertical tail, basically 5 levels of horizontal, 4 different levels of vertical, 2 different levels of mount locations, 4 different levels of velocities, you're talking about 160 experiments. That is a long range of experiments, way too much. It's the other extreme. That is very reliable, by the way. If you can do 160 experiments, you have explored all the possible cases. But also keep in mind that this is not just 160 experiments, because, for instance, each case, I probably need to do it 3 or 4 times, just to get an average of all of them. This is like to overcome the random errors that can exist in my system. So we're talking about thousands of, close to 1,000 experiments. It's way too much, too costly, but at the same time, it allows us to go through all the possible configurations. So, how do we reduce these costs, and how do we reduce the cost of the experiment? This is where the concept of fractional factorial comes into picture. Basically, we test a fraction, a subset of those all possible cases. How do we come up with those subsets? A lot of it is a lot of it can be addressed if we have a theory that we are trying to test. For instance, if you an example that I told you in class before the virus was that how is the coefficient of lift related to angle of attack? How is CL related to all the parameters such as A, cross-section area of air velocity, angle of attack, and many other parameters. We came up by doing a non-dimensionalized approach in, of course, I hope you remember from 201. We related CL to we related the lift to CL dynamic pressure, the 1/2 rho u squared, and angle of attack, and the CL hat angle of attack and cross-section area. So now we're reducing the ways, if in the past, if we had to treat u and rho as separate variables, and let's say u was taking 4 different values, rho was taking 4 different values, that's 16 different values. Now that is multiplied to the number of levels that I have to take for number of levels I have to take for cross-section area, for instance. So let's say I had to take 4 cases here, 4 here, and 4 here. That is 4 to the power of 3. That's 64 different cases. But now if instead of that, I know this relationship from theory, and I take 4 cases here and 4 cases here, I'm reducing the number of experiments from 64 to basically only 4. So I'm going to stop this video and continue in the next slide.